So part one, it should be a little bit simpler. Part one and two are divided in this way. In part one, usually it's a single object question. And in part two is where you will have usually multiple objects interacting. So in part one, it's single object. And in the interest of full disclosure, I've actually seen the question. Because I've already done so many of the freeform timed assessments, I had to kind of look ahead to see what question test student will get so that I can, re-roll the dice until we get to a question that I haven't done before. So I actually know what question I will get, but I promise I didn't have a lot of time to think about it, a lot of time to write down the solution ahead of time, and kind of doing it as extemporaneously as possible. So with that, let me get started. When the question comes up, I will start working through kind of quickly. I'm hoping to do it in like 10, 15 minutes. The time limit is 20 minutes and, it is a short amount of time. I'm trying to do it even shorter. So this is the question. It's the conical pendulum question that I saw that it got. And I haven't done it before in this setting. I've done it before, I think, in lecture. But hey, this is new. So a ball of mass m is hanging from the string of length L. Let me do this. I'm just gonna paste this in so that I can label some quantities. So the question gave us the label of L here. Ball is set in circular motion in the horizontal plane, angle theta with a vertical diagram. Yeah. Good. So A says, describe the forces on the free body diagram of the ball. And so I've seen people, draw forces directly on the diagram here, which you can, I won't, deduct the points for it. But what I really prefer with the free body diagram is a separate diagram. Because it's a graphical problem solving tool. You don't want to clutter it up with other stuff. It's really meant to be a diagram of forces. So I use a simplest possible representation of the object. At this point, it's a dot. And I draw the forces on the object. I know there must be gravity because there's always gravity unless it's way out in space. So with the gravity there, then I'm thinking through, did I draw all the forces? I know this ball is not accelerating downward, so I must have missed the force. And as I think about that, I realize, there's a string attached. That's probably exerting some force. So let me draw the tension force that's pointed that way. And if you want some geometric things, that will help you with the next steps. So of the standard strategy, this is step number 1, draw free body diagram. Step number 2, define coordinate axis in the direction of acceleration. And that's the one tricky thing about questions like this. With questions involving circular motion, figuring out where is the acceleration and what's the direction of acceleration. I can imagine someone thinking, acceleration is this way. No, if that's the case, then what's your gravity doing? It's wrong. So after you think through, really the answer should be the acceleration points towards the center of the circle. So in this drawing, this dotted line representing the horizontal view of the circular path. Center of the circle is here. Acceleration is towards the center of the circle. So that's the direction of acceleration on this free body diagram, which means I should be defining my axis this way. Plus x in the direction of acceleration and y perpendicular to it. So that's step number 2. But before I go too far, let's just finish A. It just said describe the forces on the free body diagram. Let's just do that. We have 2 forces, gravity mg, and tension force T, probably to be solved later. And I guess the model answer would be where you describe the directions. mg is directly downward, T points along the string. So that's A. B, given the angle theta, the string makes it the vertical, find the speed of the ball and the radius of the circular path. So we call standard strategy for a reason. It's the strategy you would be using basically no matter what the question asks you. That's why even before I read part B, I was going through these steps. So I did step number 1 to define the coordinate axis. Step number 3, now I need to break forces into components. according to this axis, there's only one force, tension, that needs to be broken down at all into x, into the x component of tension and the y component of tension. And hopefully, as you look at this triangle, you've done enough triangle exercises by now. You can get the expressions for tension at Tx and Ty easily enough. Let me just write it down. Tx should be equal to the hypotenuse, T, times sine theta, because it's the opposite to the angle. Ty should be equal to T cosine theta, because it's adjacent to the angle. Don't automatically associate x with the sine and y with the cosine, or vice versa. Draw the triangle, follow the triangle. So that's step number 3. Step number 4, write down Newton's second law equations. Oh, by the way, let me label B. And this is also B. So Newton's second law equations, you're writing down net force in the x direction divided by mass is, let me write the net force first. So the net force is, well, in the x direction, there's only one force, Tx. So you have T sine theta, and this whole thing divided by mass should be acceleration. And here, let me just add one more thing, because we've already argued that there should be an acceleration based on the fact that it's a centripetal acceleration, circular motion. So if it's a centripetal acceleration, we already have a formula for it in terms of other kinematical quantities. This centripetal acceleration is v squared over r, where r is this distance here. So let me rewrite that a acceleration as it's a tangential speed v squared over, let me write it as r for now. And I think, and in fact, it says find the speed of the ball and radius of the circular path. So maybe I can just keep it as r. We'll see. That's the first equation. And as you look at it, you should see you don't have enough equations because you don't know tension force. You are given the angle theta, that's good. But you don't know v, you are not given v. And you're also not given r. You have one equation, 3 unknowns. That sounds terrible. So let me keep following the standard strategy. Step number 4, you write down Newton's second. We are still in step number 4. We are halfway through. We have to write down Newton's second law for the other direction, net force in the y direction. This time there are two forces, the y component of tension, Ty, and gravity energy. So let me write it down as y component. T cosine theta minus mg, the whole thing divided by m should be equal to acceleration, and in the vertical direction, acceleration is 0. That's really the entire purpose of defining our coordinate system this way. So this equation fortunately didn't introduce any new unknowns. It's got t as an unknown, but we already labeled it. We still have 3 unknowns, but we only have 2 equations. So you gotta figure out what am I missing, and I guess this is where standard strategy leaves you. So as questions get harder and harder, you will find that standard strategy doesn't actually solve the question for you. That's never its intent. Really, the purpose of the standard strategy is to give you a systematic set of steps to follow, so that wherever you end up at the end of the standard strategy, you have some idea of what to do next. So we've been looking for equations 1 and 2, hoping that we'll have exactly same number of equations as the unknowns, and we can solve for that system of equations. And the difficulty we run into is we have 1, 2, 3 unknowns and only 2 equations. So you gotta look at the question more carefully, think about it, see where else you can come up with that additional piece of information. And hopefully after not too much staring at it, you should come to the realization that, oh, we were given this geometry of this setup, and we never made the explicit use of that. Geometry of this setup actually means you can draw this connection. L, the hypotenuse, and the r opposite to the angle theta. So r, the opposite side, is equal to L sine theta. So this third unknown r didn't really have to be unknown. We can plug this in, treat it as a known quantity. So let's do that. I'm gonna write the rewritten version of these two equations. Then 1 prime becomes, let me move m over. So it's gonna be t sine theta is equal to mv squared over, and instead of r, it's L sine theta. Oh, that makes me worry, but we'll continue. 2 is the same, but let me just rewrite it in the similar form. T cosine theta minus mg is equal to 0. So what are we being asked for? We are being asked for angle and the speed. Oh, so we need to eliminate the... We are not given the angle. Oops. I've been treating angle as known. Are we gonna be fine? No, given the angle. Yeah, we are given the angle. Okay. We are looking for speed, v, and the radius of the circular path. So I think radius of the circular path, we already know. So let's just write it down so I'm not confusing myself. Radius of the circular path is equal to L times sine theta. So I think it might have deliberately not asked you for tension to confuse you. Okay? Tension is an unknown. But what we can do is we can just eliminate the tension and just solve for V. That'll give us an expression for V in terms of all the known quantities. So solving the second equation for tension, just because it's a little bit simpler, T is equal to mg over cosine theta. I invite you to double check my algebra, make sure I didn't make any mistake doing this in my head. Plug this into equation 1, you get mg sine theta over cosine theta, so tangent theta is equal to mv squared over L sine theta. Masses cancel out, great. We are given that, but it's fine. Let's solve for v. V is equal to square root of, and I'm combining L sine theta with the g tangent theta. So Lg, there are different ways to write it. Let me write one version, sine theta times tangent theta. You could also write it as sine squared theta divided by cosine theta. So that should be the speed of v. So we say speed of v is equal to square root of L times g times sine theta times tangent theta. That's all in terms of known quantities. It's fine. We can plug in numbers whenever we need to. In fact, I think that's PHYS. Given the length of string and speed of the ball, what is the angle theta that makes? Yeah. All right. Let's just type stuff in. We need wolfram alpha. So square root of 1 meter times g, 9.8 meter per second squared, times sine of theta. Oh, wait. I gotta do more algebra. PHYS isn't asking for speed of v. It's giving you speed of v, and but I think I can actually do this in wolfram alpha. So let me do this actually in wolfram alpha. So what I'm doing is so I can have wolfram alpha solve for this. So we'll say sine of theta times tangent of theta, and we will say, that is equal to v. 1 meter per second, and we'll say take this, solve it for theta. And I think wolfram alpha should be able to do this. Solve this for theta. And yeah, it's actually a pretty complicated expression, but yeah, I think this is all right. Let me just get an answer here. So, or can I? No. Let me just do this in a calculator. Sorry. I'm wasting a lot of time. So I want the thing under the square root to be positive. So I believe this is the thing that I want. So let's do it this way. So 0.45 times 0.5 times square root of 2 times square root of 0.000108 divided by 1 plus 0.041643 divided by 1 minus, actually close the square root. Were there two square roots? No, minus 0.0208247. Okay, that's a positive quantity, arc side. That should give me the answer, 18.14 degrees. Let me put that in. That's gonna be 18.14 degrees. And I'll paste in the work later. Let's see, how much time? 3 minutes. And see, attach the work. Suppose that you start moving the ball faster so that the angle that the string makes is 3 times the value found above. What is the speed of the ball now? Okay. Oh, then I can go back to using this formula that we've already derived. So going back to using the formula, let me just do another Wolfram alpha thing. I'll just curate them later. Square root of 1 times 1. Yeah, I'm just going to keep everything in basic SI units. So sine of, so 3 times that value. So I'll just do 3 times 18.14. 3 times 18.14 degrees times tangent of 3 times 18.14 degrees. And the thing that this is supposed to illustrate is that your speed isn't exactly 3 times. It's more than 3 times. 3.34 meter per second squared. So V is equal to 3.34 meter per second squared. Then basically, angle will max out at 90 degrees, while the speed of V will approach infinity within classical physics anyway. So, all right, that's it. Let me add the work. So I have the main work of me following standard strategy. That's really the most important part of the work. So let me attach that first. And once that's done, then I'll figure out how to attach the work via Wolfram alpha, which I was allowed to use. I'm just using it like a calculator, even though it's doing some algebra for me. And I'll attach work from Wolfram alpha in a kind of comprehensible way. So I think I need to make this go away. And then I can have my different iterations of Wolfram alpha. So I think this is a first one, where I'm basically having Wolfram alpha do the algebra for me so that I don't have to. Doing that algebra, I think in the solution key does it. So you are welcome to take a look at it. It does take using quadratic formula, as you might guess from this square roots that you see all over the place. I think, let's see. There's my, there it is. So this is my other work. Somehow, copying and pasting thing didn't work, so I had to type it in manually. And then finally, this is my last work for C. This is really poor quality work. I think in some of your problems and assessments, I give you feedback. Hey, if you're just telling me what you plug into calculator, that's not complete work. That comment would apply here. Again, my advice to you is take time to organize your work. Don't do what I'm doing. This is not the best practice of what you should be doing, attaching work for your timed assessment. All right, we barely have enough time. Yeah, so I won't be able to do the next part, but okay, so this is submitted. Again, you have additional time to attach work, so you do not have to do work attaching in a kind of hurried way. Like, even if you went past this screen, you'd save the work and continue. And if you are in review work, then it won't allow you to change anything here. But if you simply refresh this screen, then you can click on add work button and still change it. It'll timestamp it, but the timestamp doesn't, I don't really pay much attention to that unless it comes after I've done the grading. So let me do this just in case maybe I made a mistake. Let me bring in my instructor view and make sure that there's no mistake. Let me find this work in my instructor view. So I'm gonna go to gradebook, the test student work. There are some people who've completed this already, but I want to be mindful and make sure I'm not clicking through anything that someone's done. Okay, Freeform time assessment part 1. So yeah, these are the questions. This should be right. No reason for this to be wrong. This also should be right. I recognize the answers kinda. They felt right to me as I was writing. Yeah, LG, yeah, that's correct. The main thing I'm not 100% sure is this. One, I didn't do the algebra. Wolfram Alpha did. Maybe I copied it wrong. And did I copy something wrong? 17.96 versus 18.14. Oh, you know what? That's probably the difference between using G equals 10 versus using G equals 9.8. So I think, round it to 18. So I think this is actually correct. Even more correct using G equals 9.8. Your answer key will just have answer based on G equals 10 because that's what the question said. But, either are fine. So this should be, 3.34 should still be about right. New angles, yeah, good. So good. All right. So that's this attempt. And sorry, there wasn't time for the second part. Maybe I could do the second part next week. I realize it's after it would have been due, but I got nothing better to do next week. So this is the second part. We'll do it in next week's virtual class session, so that I continue to add to the examples we have. So we'll just do this next week, not today.